So, section 1.5, and basically the rest of chapter 1 is dealing with linear equations, linear functions, linear inequalities, just finishing all the linear stuff. So for now, linear equations, and we all know and love these linear equations. I'm just going to do 2 examples, and well, maybe 3. So here's the first example, pretty straightforward. If you were asked to solve this equation, 3 times x minus 5 plus 6x equals negative 11 times 2x minus 11 plus 1, would you have any difficulties solving this equation? And I'm glad you're going sideways. So how do you solve that? What do you do? Distribute 3x minus 15 plus 6x equals, distribute that, negative 22x plus 33 plus 1. Combine like terms. So 9x minus 15 equals negative 22x plus 34. Right? And that's all right. So and then in this fashion, group stuff around, plus 22x plus 22x plus 15 plus 15. So we end up with 31x equals 49. Right? Then divide by 31. X equals whatever that is, or 1 and 18 31st, right? And you really have to pay attention to the form that your answer should be when working on that MyMathLab. They get a little picky, but they'll tell you, put your answer as a mixed fraction, or put your answer as a decimal. So when they mean give us an exact answer, that's never a decimal. That's with the square roots or whatever. Okay, so be careful. I know you probably already tasted the wrath of MyMathLab for not, giving a correct answer, but rather in a different format. So read that little blue thingy under the problems that tell you the format. Okay. Happy? Happy. Fractions? Fractions. All right, let's do one with fractions. Did we do one with fractions already? If I started throwing fractions all over that thing, did we try one? Okay, so let's have fun with this one. Plus 7/8 equals 5/6x minus 1/4. So, as far as the level of complexity of this problem, it's actually better than the one before. No parentheses. None of that. But what makes this problem a little harder is, well, all those fractions. Okay? So how would you like to proceed?
Clear the fractions.
Clear the fractions. I like to hear that. Because this is really what you want to do. You don't want to be moving 5/6 to the left and 7/8 to the right and adding fractions. You want to clear the fractions. How would you do that?
Common denominator.
Yeah. We would find the common denominator for all fractions, which in this case would be 24. And then I would just go ahead and multiply both sides by 24. Is that legal? Yeah. And then see what happens. When we distribute 24 through the first set of parentheses and 24 through the second set of parentheses, what happens when you multiply 24 by 2/3?
You get a whole number.
Yeah, you get a whole number because 3 reduces with 24, right? Do you all see that? I'm going to write this down. You don't have to. This is an intermediate step. You should be able to do this. This is 7 in your head. This is a completely useless step. This is just to show you what's happening behind the scenes. Because really, 3 3 goes into 24 8 times, right? 8 goes into 24 3 times. 6 goes into 24 4 times, and 4 goes into 24 6 times, right? And in one move, we do not have any fractions. We're left with 8 times 2 is 16x plus 3 times 7 is 21 equals 4 times 5 is 20x minus, which appears to be 6. So that's the big thing here. Every time you're faced with a problem, with an equation that has fractions, clear them up. Okay? It'll make your life a whole lot easier. Yeah? So then it's easy, right? Subtract 20x, subtract 20x, subtract 21, subtract 21. Oops, not here, here. So we get negative 4x equals negative 27. So x is 27 over 4. Negatives cancel. So 6 3/4. I have a feeling I did the same very problem last week. Did I? No, it's okay. Maybe in another class. Any questions on this approach? Okay? No questions? Happy? All right. Well, let's use same idea on this problem. This problem just made it up on the fly with another class earlier today, and it just worked out so beautiful, I almost cried. Because I was throwing those numbers on the board with a desperate hope that something happens in the end, and it did happen. So, yeah. All right, so there is very little that looks linear about this equation, right? It's very much nonlinear equation, the way it appears. It's got denominators, variables in the denominator, it's got exponents, but the message is still the same. When you have fractions, find the least common denominator and clear them up. What would be the least common denominator here?
X minus 2, x plus 2.
That's right, it's x minus 2, x plus 2. Because the thing on the right, that's the difference of first formula. That factors into x minus 2, x plus 2, so it doesn't contribute to the LCD. And then we'll do the same thing. We'll multiply both sides of this equation by the least common denominator. That's still legal. But now, when we distribute this entire thing. Goes multiplies the first term, and the entire thing multiplies the second term. So, when you multiply the first term, something will cancel, right? That term, that x minus 2 in the denominator, will cancel with the x minus 2 that's on the outside. Do you see that? So if they do cancel, what's left?
X plus 2 times
X
1.
times 2 plus 1, which is x plus 2, right? So I'm just going to write that. X plus 2. When you do the second product, what is going to cancel?
X plus 2.
X plus 2. And what is left?
X minus 2 times 3.
And a minus, right? So it's a negative 3 times x minus 2. Do you guys see that? When you go second, the denominator cancels with the same term, and then see what's left. Now on the right, that whole term cancels, and you're just left with a 4. Is that okay? Any questions on this? You see how that happened? I'm skipping that step that I did earlier when I wrote it out. But if you write it out like that, you will see how those denominators all go away. And then you see what's now it's very much linear equation, right? which is easy to solve. Now, by the way, what do we mean by solving an equation? What are we looking for?
Most simplified.
Yeah,
Okay.
sure, most simplified version of it, but we're looking for the value of the variable that satisfies whatever was above. That turns the original equation into an identity, right? You plug in a 7 and it spits out like 2 equals 2 that we have. Okay? So let's continue here. So x plus 2 minus 3x plus 6 equals 4, right? Combine like terms, negative 2x plus 8 equals 4. Subtract 8. Negative 2x equals negative 4. So what is x?
X equals 2.
Right, so divide both sides by negative 2, and we get x equals 2. Right? Everyone's happy? Nobody's unhappy? I'm a little bit sad. Because, again, we know that whatever we get for an answer is supposed to satisfy the original equation. The original equation. Well, if x equals 2, can x equal 2 in that original equation? What happens when x equals 2?
0 in the denominator.
0 in the denominator. So when I plug x equals 2 back in this equation, I get an explosion, right? Nothing works. So x equals 2 doesn't work here. So the only possible solution that we found does not satisfy my original equation. So what is the conclusion? No solution. This equation has no solution. Okay? So any solution, if we got 2, that doesn't work. If we got negative 2, that wouldn't work either. But any other number but 2 or negative 2 would work here. Okay, we don't have to really check. We just have to make sure that denominators do not turn into 0. Because it would give me a nonsense statement. And I want to have a true statement. Okay, so turns denominator into 0. So no solution. So that's a good problem. I was so happy earlier today that it came out like that. As I was solving this, oh, what would be awesome if the answer was 2. It's a good moment. Okay. Any questions on this? All right, good. Now, in this section, in section 1.5, our book throws this definition at us, which is a little bit premature, but I'll share it with you, and it will come back later in like chapter 4 or chapter 3. But the definition of a concept called zero of a function. What it means for a number to be a zero over a function. And basically the definition is x equals c is a zero of function f if and only if f of c equals 0. Write this down and I'll talk about it a little bit. Probably it's a little confusing at this point. So basically, whatever turns your function into 0, whatever the value of the variable that turns your function into 0 is called 0 over function. Okay? Now, this whole bit, if and only if part, have you seen those statements before? What does that mean, if and only if?
If and only if.
Right, good. If and only if means if and only if. It means two-way street. One implies the other, and the other implies the first. So if f of c equals 0, then c is a 0 of a function. But also if c is a 0 of a function, then f of c equals 0. So it's a two-way street. If then statement, it's only one-way street. Okay? But if and only if it's a two-way street. Works both ways. Does that make sense? And then we have to specify that when you start talking about logical statements and those types of if-then things. Like I make a statement, if it's raining, then there are clouds in the sky, right? Nice and pretty, and it's good, right? Yeah, if it's raining, there better be clouds in the sky. But if I flip that statement, it doesn't have to be true, right? If there are clouds in the sky, then it's raining. Oh, well, not necessarily. So that's not a two-way street. So if then has to work one way, but doesn't have to work the other way. But if and only if works both ways. Now, as anything else in math, we're pretty lazy. We don't like writing if and only if. There is a short form of if and only if. Have you guys seen that? It's if. So when you see if with two f's, that means if and only if. We just don't like writing those long statements. So that means if and only if. So if I write if, that means two ways. Okay. But for example, very simple example of what it means for something to be a 0 of a function. If I just give you a function, something simple like that, and I ask you, find all the zeros of this function, so you're just looking for the x value that turn everything into 0, which would be what? Negative 1. So x equals negative 1 is the 0 of that. You can have more than one, depending on the function. And later on, we'll start talking about is how well 0 of a function is basically your x-intercept. We'll connect it into a very nice, pretty theory. There'll be like 4 things that all mean the same. So it's going to be like really if to the power 4 type of thing. 4 things that all intertwine and imply each other. Okay, so that's all I wanted to say about that. It will come back in later sections. But now we're going to talk about maybe a little bit of word problems. Just a little bit. The ones that result in linear equations. And we'll just do a few out of the book. And the book goes into different types of word problems. So I assume a few things that you already know, like, if there's a problem that discusses perimeters and the areas of, rectangles, you're kind of familiar with all that. If there is a problem that's dealing with, rate and distance, I'm driving 60 miles an hour for 3 hours type of thing, you're good with that too. Like, you're familiar with the distance equals rate times time formula, right? Distance equals, okay. Now, the formula that I'll give you today is called the simple interest formula. And the interest, we'll come back again later. We'll have 3 ways to compute interest in this class, and we'll just start with a simple interest in this chapter. And when we get all the way to exponential logarithmic functions, we'll talk about another types of interest formulas. But the simple interest is just that. It's simple. It's easy to compute. The interest equals P, which is the principal, your initial investment or initial amount, whatever, times the rate times the time. Okay, so that's just computing the interest. So interest equals principal. So that's the initial amount. R is the rate, and T is the time. Now, when you plug everything into the formula, you have to make sure that the measure of rate matches the measure of time. If, let's say, the rate is 5% per year, then time should be in terms of years. If the question was, how much interest you earn after 6 months, then T is half a year. Does that make sense? You have to match the rate with the time as far as the unit of measure. So So let's try a word problem. And I'll pull it out of your book. But how do we solve word problems? You know, what's the first thing you have to do? What? Read it. That's good. And it's probably the most important step, which quite often we omit it. You know the second step? Read it again. That's the second step. You know the third step? What? Almost. I like my third step to be repeat step 1 and 2. And then you can start writing stuff down, see what's going on. You can change, I like changing names in the problem, so I put like people that I know, so I can relate to that problem, put myself in there, because otherwise you don't care. And I tell this story in my classes, and I told her earlier today, and so that means I'm not going to do that to you, because I'm giving a heads up. But a few years ago, I put a question on the final that was pretty lengthy, about half a page long story problem with some pretty complex, I was introducing new ways of doing things, and I feel like I was going to ask you to do things using those brand new ways of doing things. But somewhere in the middle of that word problem, there was a sentence that said, to get partial credit on this question, write your name down. And then I kept going with the crazy ways of doing things, and at the end it said, to get full credit, put a smiley face. So all you had to do is write your name down and put a smiley face, and you get full credit for the question, and about 80% of the students just left it blank. So you've got to read the problem. Okay? Never ask you to do anything else but to write your name down and put a smiley face. So that means I'm not going to do that to you then. You didn't warn. So let's do a few problems. Now, this is not necessarily dealing with the interest. Let me put this down and find that question. Is that not going to work on me? It's not going to work. Don't worry. Let me find that question. So, the problem that I want to do first is question 46 in your book, and I'm going to do this. And I hope you, oh, that's trouble. Okay, so I'm going to try to do this. Isn't that cool? Then I have to go and move it on that. All right. So you can start doing steps 1, 2, and 3. By the way, you can do this problem almost in your head without really writing down equations. They're very easy numbers in here. But you know, if I change 1800 to something more fun, and I change 1600 to something more fun, and make that percentage a little with a few decimals in it, then you have to do an equation. Otherwise, you're stuck. But does the story make sense? Did you change the name? No, you don't have to. So what was going on in here? What's the story? Can you paraphrase it? Anyone? Sure.
She gets 2 choices, you know, $1,800 a month or $1,600 a month.
Okay, good. So, hang on a second. Choice 1 is 1,800 flat, right? And choice 2 is a little more involved.
She gets 1,600 plus 4% commission, which is $40 every. Is it 4% of 1,600?
Yeah, but it's not off 1,600. She gets 1,600 as her base, but 4% of the future of the furniture. that she sells. So it's 1,600 period plus 4% of whatever it is she sells, which we don't know, right? And that's the question. For what amount of sales will two choices be equal? Okay? So that's the thing. So we should toss in a variable maybe. What do you think the variable should be?
The amount of sales.
Good, the amount of sales. So that's very good answer. Usually if I ask you what the variable should be and you tell me X, then that's a bad answer. I want to know what that variable represents. So good. What you call that variable is totally up to you. You can call it X, you can call it S, whatever. So let X be the total sales. Then the choice 2 would be what? She gets 1,600 no matter what, plus 4% of the total sales. Well, how do you express that algebraically?
0.04 times x.
0.04 times x. If x is the total sales, 4% of that, 0.04 times. All right. And now, what are they equal? So that's what you said. Choice 1 equal to choice 2. Set those two things equal to each other. So 1,800 equals 1,600 plus 0.04 x, and you solve for x. Do I have to solve for x? You all know how to solve this for x? Should come out to like 5,000. So if she sells 5,000 worth of furniture per month, she's happy. If she sells more, she's more happy. If we were talking inequalities, we'll control inequality. When that get bigger, so for $5,000 and more, she gets really happy. Does that make sense? All right, good. Let's try another one. Now, the other one will be with interest. So that will be the question 64 in your book. So we go find that one. So here we go. Student loans. All right, start reading. Does the story make sense? Did you change the name from Dimitri? Again, you don't have to. It's just so who can tell me what's going on in there? What is the story? Does the story make sense? Can you tell me what the story is about? Can you relate to that? I mean, you can totally relate to that story. By the way, your interest on your student loan is not computed in that simple interest way. It's a little more aggressive, let's say. Unfortunately. Anyone like to tell me what Dimitri's up to?
Oh, it's up to student loans.
Yeah, it's up to student loans. Up to 2 of them, 9,000 total, right? One at 5%, one at 6%. We have no idea how they're split, right? But the total interest at the end of the year is 492, right? That's how much interest whoever's going to take from him. So the question is, how are they split? Okay? Does that make sense? Can you all relate to that? Do you have student loans? Yes, no? So, I have student loans. I have a cousin named Dimitri. I don't know if he has student loans. He's a brain surgeon now, which kind of, you cannot sarcastically go like, who do you think you are? Brain surgeon? Yeah, kind of am. Yeah, that's,
Kind of.
yeah, and he's a younger too, so trouble. Anyway, so we need a variable. What the variable should be.
Do you need two variables?
That gets really messy if I have two variables. But I can sneak around. Because, well, what do you think the two variables should be? What should they represent?
The loan, each loan.
Each loan, right? So let x be loan 1, let y be loan 2. But what happens if you add x and y?
Equals 9,000.
9,000. So if loan 1 is x, then I can say loan 2 is 9,000 minus x. Right? So I can avoid having two variables, because if you get two variables, then, I mean, because technically I have two equations then. Now x plus y equals 9,000, and whatever else I can come up with. But in this case, I can just say this. Let's say loan 1. So what do we know? The interest, I'll just call it R, is 5%. The amount, let's call it X dollars, no idea how much. The time, in this case, is kindly just 1 year. That makes it a little easier. Now, loan 2 is 6%. The principal now is 9,000 minus X. So you really want to avoid giving a second variable. I mean, later we'll do problems with multiple variables. And time is still 1 year. So, but the problem is dealing with the interest. So we need to figure out what the interest is. Well, what is the interest from the first loan? So call it I1. It's principal times rate times time. So it's x times the rate, 0.05, times time, which is 1 in this case. So we get 0.05x. So that's the interest just from the first loan, the 5% loan. From the second loan, so let's call it I2, the principal is 9,000 minus x. The rate is 0.06, and the time is 1, or in other words, 0.06, 9,000 minus x. Is that okay? So those are the two expressions representing the interest from the first loan and the interest from the second loan. But we still don't have an equation. How can I build an equation out of that? What else do we know about the interest?
He owes $492.
Yeah, so the total interest for the year is 492. So if I add these two quantities, I should end up with $492. So I1 plus I2 equals 492. That's given, right? So then just fill in the blanks, 0.05x plus 0.06 times 9,000 minus x equals 492. And that is a linear equation, right? And I don't have to get rid of those fraction limit decimals. We can deal with that. I can just start solving this thing. So 0.05x plus 0.06 times 9,000 is 540. And then you go that way, it's negative 0.06x equals 492. Combine like terms and subtract 540. So 0.05 minus 0.06 is negative 0.01x equals, looks like negative 48. Okay. And divide both sides by negative 0.01. -0.01, we get x equals 4800. So that's the how much was borrowed at 5%. So how much was borrowed at 6%?
42.
42. 42. Right? Because you still have to make 9,000. So then the answer $4,800 borrowed at 5% and 4,200 borrowed at 6%. So how is that? Does that make sense? Happy? Good. All right, let's talk linear inequalities. So that's section 1.6. Linear inequalities are really friendly. Any other type of inequality is a big pain in everywhere. And we'll deal with that. We'll deal with the so-called nonlinear inequalities. They're a lot trickier. There is no real algorithm of solving it. There's a lot of testing and a lot of thinking. While linear inequalities, it's just like solving equations. You're just trying to get the variable by itself. But there is a little bit of a area that you have to be careful about. Because sometimes whatever the inequality sign you had in the original problem, sometimes you have to flip it. Do you know those instances where the inequality sign has to be flipped?
Divide by negative.
Divide by negative, multiply by negative. Those are the two big ones. Okay? But everything else, just like with solving equations, all those operations, adding, subtracting, will not change the inequality sign. Multiplying, dividing by positive numbers will not change the inequality sign. So I'm going to write all that down. So things that don't change the inequality sign. So adding, subtracting, same numbers from both sides. Okay? One way to argue that, if you have two numbers, one is less than b, I'm sorry, a is less than b, right? So on a number line, it means here is a and here is b, right? A is less than b. Well, if you add a number to both sides of this inequality, that means a jumps this way, but b jumps the same way. So the relationship between them stays the same, right? If you subtract, same number from both sides, a jumps that way, but b jumps the same way. So the relationship between a and b remains the same. A is still to the left. That's kind of a cute way of thinking about that. Is that all right? Okay. I'll do the next one numerically, but I'm not sure how to make those jumps. 2 multiplying, dividing by positive numbers. So the big thing here is the word positive. And if I just do a numerical example, if I write a statement, let's say 3 is less than or equal to 7. Is that a true statement? Yeah. And if I just multiply both sides of this thing by, let's say, 2, I'll end up with 6 and 14. Right? So inequality still faces the same way. Do you agree with that? With the division, kind of same thing. If I say 9 is greater than 6, and then I just divide both of them by, let's say, 3, just divide by 3, I'll get 3 and a 2, 3 is still greater than 2. So dividing, multiplying by positive numbers is okay, nothing changes. Now, when you have to reverse the inequality is when you multiply or divide by negative numbers. So we have to reverse the inequality. We have to reverse the inequality sign when multiplying or dividing by negative numbers. Right? Yeah. So for example, 2 is less than 5. Right? But if I multiply both sides by, let's say, -2, we'll end up with -4 and -10. Which one is bigger?
-4.
-4. So inequality got flipped. And same thing with division. I'm going to do an example. So you have to remember that multiplying, dividing reverses the inequality. There is another instant that you might run into when solving linear inequalities where the inequality has to be flipped, is when you take reciprocals of both sides. Okay? So you have two sides of inequality and you just turn them into fractions, see what happens. Same kind of example, 2 less than 4, right? That's true. But if I flip them, I get 1/2 and 1/4. Well, 1/2 is bigger than 1/4, right? So taking reciprocals reverses the inequality. You might see this on an occasion, but not a lot. Okay? There are other instances where the inequality gets flipped. Sometimes if you start squaring both sides and things like that, but we never do that when solving linear inequalities. And we never do that really when we solve any types of inequalities. So that's, we don't need to know that. There are other instances. But these are the ones that we will use. Yeah? Good? Let's do one. For example, solve the inequality. Oh, he's at a break time. That's probably break time. Yeah, let's do a break. That's already 50 past the hour. And we'll come back. All right, so let's do this. Here's an example. 13 minus 7x is greater than or equal to 10x minus 4. So again, we think of this problem just like regular equations. You just solve it. You want to isolate x. So if this was an equation, how would you go about it? You know, just subtract 10x from both sides. So that's negative 17x. Subtract 13 from both sides. So we have negative 17x greater than or equal to negative 17. Okay? And then to get x by itself, divide both sides by negative 17. And now this is the time where you have to flip the inequality. So we divide it by a negative number. Now, expressing your answer. There are multiple ways you can do that, and my math lab kind of asks you, do this way, do that way. So there's an interval notation. Interval notation here. So it's everything less than 1, including 1. So it's from negative infinity to 1 with a bracket. Okay, so that's the interval notation. Set notation. Using the set notation, it's all x's such that x is less than or equal to 1. So that's the set. You're sometimes asked to graph this thing. So graph of this solution is if this is 1, everything to the left of 1. Now you also have to somehow express that 1 is a part of the solution, and your book does the bracket right on the number line. That's how your book shows that. Most of you have seen the other way, is that with the dot. If you have a filled-in dot, that means it's included. So either way, on the handwritten work, either way is fine. On my math lab, I'll ask for the bracket. So, and then usually these things are multiple choice, so you don't have to build the bracket anyway. So you'll see how they like that. So does that make sense? That flipped inequality, multiple ways to express the answer, interval notation, set notation.
What's the difference between the two graphs?
Well, to me, there's no difference between two graphs. It's just different notation. Recently, all the math books started using the brackets right on the number line, and in the past, they used those dots. And I'm sure you're all more familiar with the second option. So, again, on the handwritten thing, I really don't care. Now, on my math lab, they'll give you that as a multiple choice option, so you don't have to worry about building that by hand thing. Okay. Is that okay?
Yeah.
All right. Now, this is what we call so this is what we call a complex inequality, so compound inequality. Is when you have one statement that has two inequalities at the same time. For example, negative 2 is less than 2x plus 1 is less than or equal to 5. So we have some algebraic statement sandwiched between two other algebraic statements. And our goal right now is to do whatever is possible to get x in the middle by itself. All right? So if you're trying to get x in the middle by itself, what is the first thing you're going to do?
Subtract by 1.
Yeah. So subtract 1 all the way through. So you'll get negative 3 less than 2x less than or equal to 4. Okay? And then, in order to get x by itself, divide by 2 all the way across to get negative 3 halves less than x less than or equal to 2.
So if that was a negative 2, would you switch the signs on both?
Yeah, they'll all flip, and you would actually have to really rewrite it in a more convenient way, but yes. Now, in the interval notation, everything in between negative 3 halves, not including negative 3 halves, and 2, including 2. So we would write it from negative 3 halves to 2 with a bracket around 2. Right? So you see all the numbers that are greater than negative 3 halves and less than 2 at the same time. In the set notation, we would get this, all x's such that x is in between negative 3 halves and 2. And the graph here would be, this is negative 3/2, and this is 2, everything in between, including 2, not including negative 3/2. Or empty circle filled in, whichever way you like. Does that make sense? This is really an intersection of two sets, by the way, because we're asked to solve an inequality where x is greater than negative 3/2 and less than or equal to 2. Okay, so it's greater than and less than. Because if I do this with the magic pen really, really fast, if I think of these two sets, everything greater than negative 3/2, well, it's this set right here. But everything less than or equal to 2, it's this set right there. This is where they overlap. This is their intersection. Okay, so when you see the compound inequalities that way, when the inequalities kind of follow each other in a pretty way, like that, you're really dealing with an intersection of two sets. Okay? Now another example of a compound inequality. Um, 3x minus 1 is less than negative 5, or 3x minus 1 is greater than positive 5. Which looks like two separate inequalities, but they are glued together by a magic word or. And when we hear the magic word or, we think about what? Yeah, but try to connect it to what I was telling you about the intersection in the previous one. The union. Remember that?
Yeah.
The or connects us to the union and connects us to the intersection. So here we'll have, when we solve this, we'll have two sets going in opposite direction. Okay, they will not have any overlaps. But the or tells us, well, we need both. We'll need the union of the two sets. Okay? So anyways, I'm just going to solve them separately. 3x, add 1 to both sides. So 3x is less than negative 4. So x is less than negative 4/3, is it? Is that right? Yeah. While on the other side, add 1. Add 1. 3x is greater than 6. Divide by 3. X is greater than 2. Okay? So it's everything to the left of negative 4/3 and everything to the right of positive 2 with a big gap in between. So in order to take both of them, we connect the two sets with the union. But anyway, so the interval here would be everything from negative infinity to negative 4/3, not including negative 4/3, union with everything from 2 to infinity. Okay? So that's the solution to this inequality using the interval notation. The set notation would be all x's such that x is less than negative 4/3 or x is greater than 2. Sometimes they just use a comma in there, but or is more precise. And the graph here is negative 4/3. Everything to the left of that. And here's a positive 2. Everything to the right of that. How's that? Is that okay? Okay, good. So now, since we have made the knowledge of linear inequalities official, we can go back and find more domains of functions. Remember we did that last week? Finding domain of a function. So for example, if I write this, 3 minus the cube root of 2x plus 1. And last week we were talking about when dealing with domain of a function, we right now have two areas that we have to be careful with. Division, make sure you don't divide by 0, and even roots, even radicals, so the square roots, the fourth roots, and so forth. Everything else is okay. All right? If you do not see those two trouble areas, the domain of a function is automatically all real numbers, because everything else goes. Because I can take cube roots of negative numbers, no problems there. So in this function, do you see any trouble areas?
No.
Right, cube root, good. We're only afraid of even roots. So right away, domain of this function is all real numbers. Cube root is okay. Because I can take cube root of negative numbers. Because if I cube negative numbers, I'll still get negative numbers. With the even ones, that's where you get into trouble. So all real numbers. I'm not even going to write that to make it more fun. I'll make it 32nd root. Makes no difference as far as what kind of a root is. It's just all I see now it's even. And when I see an even root, that's when I have to be careful. With even radicals, I have to make sure that the radicand does not turn negative. Okay? Could be 0. Taking roots of zeros is okay. Just cannot do even radicals, even indexed radicals of negative numbers. So we have to make sure that the radicand stays non-negative. In other words, I'm going to take whatever's under that 32nd root. It's really irrelevant what number it is as long as it's even. And make it to be greater than or equal to 0. And then solve that inequality. The solution to this inequality will be the domain of that function. Does that make sense? So whatever you solve that, you get x is greater than or equal to negative 1/2. So that's the domain, right? Domain is from negative 1/2 to infinity. Right? But do you see what I mean? If this was just a square root, still be the same domain. If this was 12th root, it will still be the same domain. Because again, the radical does not affect the sign of what's underneath.
Is that a bracket?
Yeah, it's a bracket at negative 1/2, but it's always a parenthesis around infinity. If I take the same function and I divide it by 7, that's not going to affect the domain. Because 7 in the denominator does not really make it scarier, as long as it's not 0 in the denominator. So the domain will still be the same. Do you see that? So if it's odd radical, all real numbers, no worries. But if it's even, that's where you have to start worrying. You take whatever's underneath, make it greater than or equal to 0, and then solve. Yeah? Yeah. Make sense? Good. So I got another one for you. It's a little more fun. Because we already kind of did that earlier when we just introduced functions. But here's this example. G of x equals x plus 1 over the square root of x minus 2. So I have two areas that I need to be concerned about. First of all, I got a denominator with letters. So I have to make sure the denominator stays non-zero, right? But I also have to make sure that my square root is happy. So I want to also make sure that the radicand does not turn negative. So the radicand, that means the radicand cannot be negative, and it cannot be 0 at the same time, right? So the only difference between approaching this new question from the previous question, in the previous question I only worried about negative numbers, but here I'm worrying about negative numbers and 0. So I'm just going to say, well, x minus 2 just has to be positive, and then I'm good. So you see the difference? Instead of making it greater than or equal to 0, I'm just making it greater than 0. And it will avoid getting 0 in the denominator, right? So that's the only difference really between these two problems as far as finding the domain. That's all I'm doing. So I have to make sure that the square root is happy, so positive, and cannot be 0 because it's in the denominator. So the solution here is just x is strictly greater than 2, so that's what's going to work. So the domain, all x is such that x is greater than 2. So do you see what happened here? Before, we could get 0 under that square root, under the radical, because you can take square root of zeros. In this case, yeah, you can get 0 under the square root. Square root of 0 is 0, but you're going to end up with a 0 in the denominator, so that's why we're not allowing 0 in our inequality. Yeah?
Yep.
All right, let's try another one. A little more fun. What if I do the opposite way? What if I put the square root in the numerator and then something else in the denominator? So I got two things that are working against me. I got a square root. I got to make that square root happy. What makes square root happy? Let's just focus on the square root.
Greater than or equal to 0.
Yeah, so to make the square root happy, x plus 2 has to be greater than or equal to 0. But at the same time, I have to make my denominator happy. So and x minus 1 cannot equal 0. Right? So there are two things that are working against me right now. The square root has to be happy, and the denominator cannot be 0. Now I'm going to solve this first inequality, so x is greater than or equal to negative 2, right? And that thing is pretty straightforward, x cannot equal to 1, right? Because it's very important, because 1 is greater than or equal to negative 2. So I have to kind of exclude 1 from my solution. So the solution, the domain here would be everything from negative 2, including negative 2, all the way to 1, not including 1. And then starting from 1 to infinity. You just kind of poke in a hole in that first inequality. So on interval, you're looking at everything from negative 2 to 1, union from 1 to infinity. Is that okay? Does that make sense? So this is more of a complex situation. A little note, don't write this down, I just want to verbalize this. Does that make sense? If I make my denominator, don't write this down, plus 11, for example. So on this side, I have to make sure that x cannot equal negative 11, right? But x is greater than or equal to negative 2 to begin with, so that excludes that whole negative 11 already, right? So then I just need that part. That part solves that other issue, if that was negative 11. Does that make sense? Because then it just, from negative 2 to infinity, and negative 11 is all the way over there, so it's already gone. So let me go back, so my notes still make sense here. Otherwise, it should. Yeah? All right, that's chapter 1 for you. Exciting. Well, we're not done yet. Oh, come on, look at the time. I have you for another, and that clock's probably fast. Half an hour? No, that clock is already, this clock is fast. And this is driving me crazy, because look, if you look at my lecture, it looks like I'm always late. Look, that's 6:06, which was not the case. And I don't know why they cannot fix that. All computers here are like that. All right, chapter 2. Now we're digging deeper into functions. Linear functions are going to be something that we're going to miss. Now I'm going to start talking about this chapter by opening that book in front of you, because there's going to be a whole bunch of definitions that I really don't want to talk about or write them down. They're mostly self-explanatory. So like the very first page of chapter 2 introduces a concept of an increasing function, decreasing function, constant function. And it's exactly what it sounds like. If a graph of a function is going up on an interval, that means the function is increasing. So this first parabola is increasing at first, up to that point, and then it's decreasing. Is that okay? So there's a definition on the bottom of that page. I really don't want to write that down, it's there. So, like the next example is decreasing at first, then increasing, while this guy stays constant. So, neither increases nor decreases. Do those definitions make sense? In college algebra, we'll just go as far as look at the graph and recognize whether it's increasing or decreasing. We're not going to do any further analysis. When you're going to take your Calc 1 class, you'll be able to look at the function as an expression and dissect and predict when it's increasing and decreasing without looking at the graph. Or maybe you can graph it if you know when it's increasing or decreasing. But here, just kind of look, see what's going on. So there are examples. So you are on your own there. You just kind of read it. It's not that complex. There are a lot of words, but okay. Another concept, relative maximum and relative minimum. Again, in college algebra, we'll just want to look at the graph and be able to identify what they mean by relative maximum, relative minimum. Relative maximum meaning the highest point on the graph in relation to everything in a small neighborhood around it. That makes sense. Highest point on a small interval. So every time you see a little bump on the graph, a little peak, that's the relative maximum. Doesn't have to be the highest point. You just have to kind of go up and come down. Okay? So, like here on this graph, you see this point identified as relative max. Because relatively to everything around it, that's the highest point. Same thing with those two. Those are relative minimums. In relation to everything around those points, those are the lowest points. And here the definitions, they made them official. But again, in this class, we're just going to be, look at the graph. Oh yeah, that's the clearly relative maximum. Whatever. Every time you see a bump, that's the max. Every time you see a little valley, that's the min. Is that okay? So basically, the first few pages, applications, yeah, we'll talk about that. I want to talk about very special family of functions before we stop today. So more on functions here. I want to remind you of a very friendly function, the absolute value function. F of x equals absolute value of x. All right? And I'm going to ask you to compute this function at some point. If I ask you, what is f of 2 equals to absolute value of 2, what is that? What does that equal to? 2. If I ask you, what is f of 0, what is absolute value of 0 equals to? 0. And if I ask you, what is, let's say, f of negative 3, absolute value of negative 3, that equals to? 3. 3. Good. Very good. You know your absolute value. And now if you allow me, I will completely destroy your confidence in absolute values. Because now I'm just going to start messing with these things. Feeling good about it. First of all, what is the absolute value from a physical point of view? What does it tell us?
How far from zero?
Right, how far from 0. So it tells us the distance from the origin. That's why it's always positive. 2 is 2 units away from 0. 0 is, well, 0 units away from 0. Negative 3 is still 3 units away from 0. That's why the absolute value is always positive. But how, now really focus on how your brain was answering those questions. I know it was basically automatic for you, but how were you generating those answers? And I bet none of you pictured the number line and started counting, you just knew what to do. So tell me, try to think how you were thinking when you told me that absolute value of 2 is 2. What was your thought process there?
Whatever number was between, just having positive.
Well, yeah, so you looked at 2, said, well, it's positive, so, it's 2.
Well, like for -3, just take off the negative.
All right, good. Is that how you all think? I bet that's how you all think. Good. Now, this whole take away the negative operation, is that on your calculator? Does your calculator have take away? How many operations do we have, by the way? Say 2. 2. What are they? You only have 2 operations. The rest of them kind of made up.
Add and subtract.
No. Add and multiply.
Add them all.
Because subtracting is adding negative numbers. Dividing is multiplying by fractions. You only have addition and multiplication. The rest is just making your life easier. Right? Exponents, that's multiplying many, many times. Square roots, that's kind of exponents. So now pretend that you are some kind of a computer of sorts. And you're trying to take away a negative from 3. That's just weird, right? And what do you have to do? What kind of an algebraic operation you have to run to take away a negative? How do you kill a negative? Multiply by -1. So that's really what's going on here. The way your calculator maybe thinks about this problem is, if you start with the positive numbers, don't mess with them, let them be. But if you start with a negative number, multiply it by -1. So it seems like there are 2 functions inside this one function. There are 2 operations that are completely separate, and they depend on the input. If the input is positive, then the output equals the input, right? X goes in, X goes out. 2, 2, 5, 5, 7, 7. But if your input is negative, a whole new operation kicks in, multiply by -1. -3 times -1 is 3. -5 times -1 is 5. So there are 2 functions hidden inside one. And these types of functions we call piecewise functions. They come in pieces. The function changes its definition depending on whatever you put in. Kind of with me on this one a little bit? All right, good. We're having fun. So, the notation for the piecewise function, that's what we call it. Piecewise function is this. We have this big bracket, and our function is -x if x is less than 0, and it's just x if x is greater or equal to 0. And I'll write this down, and I'll talk in a minute how this notation. First of all, some of you might have seen this notation before, which is okay. So these inequalities on the right, x less than 0 and x greater than or equal to 0, they act like a filter. You throw in the value, and these inequalities will tell you which part of the function you're dealing with. Okay? So this is more like a filter. Okay? And the way that works, if I go back and ask you, what is f of 5, or in this case, what is the absolute value of 5? You look at this expression. Let's say you've never dealt with absolute value, but you see this. You look at this expression and say, all right, x equals 5. Out of these 2 inequalities, which one x equals 5 satisfies? The bottom one, right? X is greater than 0. 5 is greater than 0. So therefore, this is your function, just x. So the value of this function is whatever your x was. So in this case, it's just prime. You see how that works? The value of the variable defines which piece of the function you're dealing with. At the same time, if I ask you what is f of -7, you go, all right, x is -7, which inequality does it satisfy? So it's the top one. -7 is less than 0. Therefore, negative x is your function. Negative of -7, which is positive. It's kind of a weird way to think about absolute value, but this is the simplest example of a piecewise function. The worst thing I've seen students do with piecewise functions is when they plug the value in all pieces, giving me multiple results. That tells me, I don't know why they're so loud. That tells me two things. First of all, you don't know how the piecewise function works, which is not the biggest problem. Biggest problem is that you have no idea what the function is. You cannot put the same value and get me different results. Right? The functions don't work like that. One input, one output. So, let me do an example of a more complex piecewise function, and we'll just try to evaluate the values in it. X squared minus 3 if x is less than -1, 2x plus 4 if x is between -1 and 2, including -1, and 7 if x is greater than or equal to 2. So this particular function comes in 3 pieces. Okay? And by the way, we meet piecewise functions in real life quite often. Like if you think about your electric bill. Anybody get an electric bill?
Oh, yeah.
They know that the electricity, they charge it differently depending on the usage. Like the first few usually cheaper, because you got to run your refrigerator and your water to survive. But as you get your gaming on and your 50-inch or whatever, and AC and the hot tub, those things get more expensive. Okay? So it's kind of a piecewise. Depending on the region you're in, they charge differently. Your cell phone bill, you have, kind of a flat charge for first, whatever minutes, and then you start going over, they start bumping you up. So those types of things happen. But for the sake of just playing with that, if I ask you, what is f of 0? And again, the way you think about this problem is, all right, the value of x is 0. So you look on the right, which one of those 3 inequalities does 0 satisfy? So which one is it?
Middle.
The middle one. So since x equals 0 is between -1 and 2, then 2x plus 4 is your function for that value. All right, then you're dealing with 2x plus 4. That's where you plug in 0, 2 times 0 plus 4. And you only get 1 out. Okay? Does that make sense? If I ask you what is f of -1?
In the middle.
Again, in the middle. Because x equals -1 is in the middle, so it's 2 times -1 plus 4. So -2 plus 4 is 2. Okay? You with me on that? How about f of -5? Which one? Top. Okay? X is -5, which is less than 1, so we're dealing with the top part of this function, so it's x squared minus 3. So in this case, it's -5 squared minus 3. So it's 25 minus 3, which is 22. Oh, Lance just joined us. Hi, Lance. I think Lance is in Maine. Lance, is that right? Are you the one who lives in Maine? You can type in your answer. I don't think your voice works. Oh, I don't know, maybe you cannot hear me. All right, we'll get back to that. So is that all right, 22? Does that make sense? Yes, good. How about f of 10? 7, right? When you get past 2, it's always 7. It's a constant function, so it's 7. If I ask you what is f of pi, you would say Still 7. Yeah. Can you guys hear me, the online game? I haven't seen anything from you. All right. Yeah, yeah. Oh, look good, good. Having fun? Oh, I was suspecting that you just log in and like go eat dinner or something. Yeah, they're all active. Good. Oh, that's all I did with the earlier class. You guys are quicker. What's going on? Why is that? They just ask more questions and you're sleeping. That's the problem. Any questions on this? You'll see that. Because they'll try to graph one of those things. That's fun.
That'll change per question, right?
Well, right. I just made this one up on the fly.
Actually, a question on 22.
Yeah.
So isn't it supposed to work on the right side? Isn't that what? Put the -5 in the top equation because it's supposed to work on the right side.
Right, because x is -5, and I'm just looking at which part it satisfies. Right? So -5 is less than 1.
Alright, I thought you said it was 22.
Oh, no, 22, that's what you get out of it.
Alright.
Now, the value of the function could be anything and does not relate to those inputs anymore. It could be whatever. Okay? But it's all depending on the value of x, and it will tell you where it goes. Okay? Well, all right, good. So, so I guess we're done because that's how far I went with the first group, and
Sorry, Lance.
yeah, sorry, Lance, you just got in. But good for you. All right, guys, I'll see you on
See you, Alex. Thanks.
Wednesday. Yeah.